Yeah, a very good morning to all of you. We are going live. That's why, Srikanth's hand I was looking at. Of course, we have only a few audience and we hope many of your friends will join. This is a momentous occasion because the country is going through a growth trajectory and we had experienced shortage of semiconductor chips very badly in many sectors, including automotive sectors. So what was limiting is that we could not manufacture these chips. Right now, today, our Honorable Prime Minister is inaugurating first time a semiconductor manufacturing facility in India. Two places in Gujarat and also a testing facility in Assam. So this occasion, our country, we are becoming more and more proud about manufacturing. We had a limited semiconductor complex in Chandigarh, but that was only for making a very highly specialized some chips. And as all of you know, the heart of an IC is a chip. And for that, we need transistors. And for that, we need semiconductors. So had there been no semiconductors, no transistors, and no electronic devices, all this started in 1956 with the Nobel Prize of three great physicists. I hope all the students know them, right? Who got Nobel Prize in 1956 for transistor discovery? Three people. Bardeen, Brattain, and Shockley. Please look at the background, okay, in 1956. And now we are able to manufacture chips. So last 10 years, country is going through acute shortage of chips. We have been discussing with Intel to start manufacturing here. Now Micron is coming up to India for manufacturing. But we need to have our own capability. That's why this is a special occasion. So I'm glad that the country's ambitious targets about making these semiconductor chips will be fulfilled, and it will have far-reaching implications in many sectors. Transport sector, electric vehicles, what is the limiting is about availability of chips, and in many, many other computation, AI, all linked with major activities. So I am glad that ISA Tirupati is doing in our own characteristic way a short session dedicated to give you some information about semiconductors, very, very broad, generic form. I would like to thank Professor Prasenjit Sen, who orchestrated this event, and Dr. Kanakasekaran, who is going to give you a brief aspect about the historical significance of semiconductor chips. And I also would like to thank our administration, the deans, all the associate deans, dean academic, dean faculty, and also our IT infrastructure and administration to put up such a quick program, because we had a meeting with the secretary only day before yesterday. And secretary had a meeting with all the higher education institutions, IITs, ISIS, NITs, central universities, where there was a mandate that the program must be disseminated to the next generation. Because when we start manufacturing all these chips, the benefit will come after 5 years, 10 years. And you are there, the future generations. That's why we are a little bit sad that we don't have enough people, but I hope before 10:30, most of your friends, please send WhatsApp messages. They should be around, because by that time the PM comes and talks about this historical significance of this day, we would have a packed audience here. We need to upload this. It's also a part of our educational activity. With this, we have a program where we have two talks. I would like to ask Professor Prasenjit Sen to introduce the first speaker. I'm sure you know both of them because they are all our teachers. Professor Sen.
Good morning, everyone, and thank you, Professor Pillai. So these are all in-house speakers. Our first speaker, Dr. Kanakasekaran, he will talk about semiconductors. Those of you who do not know, his area of research is semiconductors and organic semiconductors in particular. So he will give us a perspective on semiconductors. And I'll give the next talk. And this event has been named India's Decade. Semiconductor is the focus, but in addition to that, India is trying to take a leap in new generation technologies, including quantum technology and machine learning and artificial intelligence. So I'll give a brief talk after this on application of machine learning in my area of research. Dr. Kanakasekaran.
Yeah, thank you. Okay, very good morning to everyone. So today I am going to talk on the semiconductor revolution, history and impact in the part of the India semiconductor mission. So first I want to classify the materials which are surrounded by us. Depending on its electrical conductivity, we can classify the materials into a conductor and semiconductors and insulators. So if the material which are easy to conduct the electricity, we used to call it as a conductors, and the materials are difficult to conduct the electricity, call it as a insulators. The materials are in between. This is the semiconductor. So for the very good example for the conductors or gold, silver and iron, these are the very good examples for the conductors, and for the insulators, the paper, glass, ceramics, rubber and polyethylene, these are the good examples for the insulators. For the semiconductors, the elemental compounds of silicon, germanium, gallium arsenide, these are the very good example for the semiconductors. So why these materials have these kind of different properties? Some materials are very good in conduction and some are not in a very good electrical conductivity, is completely depending on the interatomic spacing of the materials, in particularly the bands, the energy bands, how the energy bands are in that material. For example, in the case of conductors, the energy bands, the valence band and the conduction band, there will be an overlap in the bands. So that is the reason there will be a good electrical conduction is possible in the case of conductors. At the same time, on the other hand, if you look at the insulators, the energy gap between the valence band and the conduction band will be very large, roughly the plus 5 eV. So in this case, the electrical conductivity will be very, very less. On the other hand, if you look at the materials which are the semiconductors, have the band gap between the 0.1 eV to roughly 3 eV, we can say that. So that is the reason behind it, why the materials are, some materials are in a very good conduction and some are not in a good insulators and some are in the semiconductors. So as we all know that semiconductor is made a very important role in the field of electronics. But before we discuss about the semiconductor is not the one for the initial compounds for the electronic devices. The vacuum tubes are the first electronic components for the electronics. Okay, the vacuum tube work in the principle of thermionic emission. This is a schematic diagram of the vacuum tube. It consists of the cathode, anode, and the control grid, almost similar to our transistors. Okay, here this near the cathode, there will be a heating filament. When we apply a very high voltage to the heating filament, the cathode will heats up and it will emit the electrons, and the anode will be given as a positive potential. Then the electron, whatever the electron exciting from the cathode, will be attracted towards the anode. Then there will be a current flow in the system. So then the vacuum tubes, the first generation computers mainly made of the vacuum tubes. So if you see, this is the first generation computer. It looks very big in size, and the stability also will be very, very less compared to our present transistor based computers. And also the slow processing speed, the program processing speed will be very less compared to our present system, and the stability also will be very, very low. But anyway, with the help of the vacuum tubes, in the initial days, they have invented the computers and able to do the analytical programs also. But after the 1947, when as just now Professor Pillai mentioned that, he asked that who are the people got the Nobel Prize for the invention of the transistors. Yes, from the scientists from the Bell Laboratories, Bardeen, Brattain and Schottky, who have invented the transistors in 1947. Then after the invention of the transistors, the electronic industry has drastic change happened in the field of electronics. Okay, so almost, if you ask what are the, even though already they have invented the computers with the help of vacuum tube, but these vacuum tubes will be in a few, at least 1 feet and more than that. Okay, but when you compare with the recent developments of the transistors manufacturing, you can go to the nanometer scale transistors also possible. The first difference is the miniaturization in the size. The next one is the speed, and the maintenance cost will be very, very less when we replace the vacuum tubes with the transistor, and a lot of other environmental advantages also there. So these transistors made of semiconductor. Okay, first, what is the semiconductor? As I have mentioned earlier, semiconductor means in terms of the band gap, energy bands, if you see that there will be a band gap between, there is a gap between the valence band and the conduction band. At the 0 Kelvin, the valence band will be completely full of electrons and the conduction band will be completely empty. When you come to the room temperature, when it gaining the thermal energy, some of the electrons is gaining the energy and it makes an upward transition or excited to the conduction band and leaving the holes in the valence band. These electrons call it as a free electrons and the holes are free holes. And these electrons and hole are the responsible for the current transport in the semiconductors. The number of holes and the electrons will be equal in the case of intrinsic semiconductors, but the intrinsic semiconductors are generally high pure, but the conductivity will be very, very poor. But if we want to make any electronic devices, we need a good conducting semiconductors. For that, we have to go for the doping mechanism. So, as I have mentioned that semiconductor materials are very high pure, but the conductivity very low. We have to, even though there will be a limited number of free electrons and holes will be there, but those carriers are not enough for the good conduction. So for example, if you have considered the silicon, the well-known inorganic silicon semiconductor, which have the atomic number of 14, and when it forms the crystallization, it is possible to make a very stable crystallization is possible, but the conductive high pure intrinsic semiconductor. But if you want to use this for the fabrication of electronic devices, it is not the suitable one. So for that, for example, if you want to make the intrinsic silicon into N-type semiconductor, N-type silicon, you have to dope with the pentavalent atoms like a phosphorus, arsenic, or bismuth, or antimony. So if you dope with this, these are 5 valence electrons it has. So the 4 valence electron, it will make a bond with the neighboring silicon atom, then 1 electron will remain. Then if you increase the concentration of the doping, then the number of free electrons will be much in the system. Then these carriers will enhance the conductivity in the semiconductor. In this way, we can convert the intrinsic semiconductor into a extrinsic semiconductor with adding the impurities, then to increase the conductivity. This type of material called as the N-type semiconductor, where the majority of the current carriers will be electrons. On the other hand, if you want to convert the intrinsic semiconductor into a P-type semiconductor, we have to go for the trivalent doping, where the 3 valence electrons will be in the outermost cell. Then the 3 electrons will make a strong bonding with the neighboring silicon atom, then 1 hole will be remain. Likewise, if we increase the doping concentration, it is possible to make increase the conductivity of the semiconductor. These type of materials, you might know that we call it as a P-type semiconductors, and where the majority of current carriers will be holes. So we can generally classify the semiconductors into an intrinsic semiconductor and extrinsic semiconductors. Intrinsic semiconductor will be high pure, where the number of electron, the intrinsic carrier concentration will be equal. In the case of extrinsic semiconductor, it will be impure. The impurity will be added into that. So depending on what type of impurity you are adding, whether pentavalent impurity or trivalent impurity, we can increase the number of current carriers. In the case of N-type, the electron carriers will be more compared to the holes. And in the case of P-type, the hole carriers will be greater than the electron carriers. So whenever we want to go for the real device fabrication, we need the combination of P and N. For example, the well-known electronic components are the diode, transistors, and integrated circuits. Whatever the important electronic circuits, we need this junction between the combination of P and N. Then whenever you make the junction, there will be a junction region will form. This is the high resistance region. It's called as a depletion region. In the case of diode, there will be only 1 junction region will be there. In case of transistors, there will be a 2 junction region. These junction regions are the responsible for the electrical properties of the electronic components, whether electrical or optical property of the semiconductor devices. Okay, so further, if I want to classify the semiconductor into inorganic and organic semiconductors, most of the inorganic semiconductors are based on the silicon, germanium, or gallium arsenide, where the bonds will be covalent bonds. And in the case of organic semiconductor, most of the time polymers will be used as polymers will be used, or sometimes the small molecules also will be used for the fabrication of organic semiconductor based transistors or diodes, these things, and where the van der Waals bonds will be there in the crystal. Or the other way around also, I can classify the semiconductors. So if we want to make the, generally it's not 100% correct, but mostly if you want to fabricate the devices, only the electronic devices, so we have to go for the inorganic one. If you want to fabricate the optoelectronic devices, so the LED, normal LED is a electronic device. The light emitting diode is the optoelectronic device. So in that way, I can say that. Okay, it's not 100% correct, but depending on the high quantum efficiency. So why we want to go for the organic semiconductor? The next question will come to here. Okay, the organic electronics are lighter and more flexible. It has many advantages of low cost electronics. We don't need any vacuum processing, no lithography. Okay, then directly you can integrate because of the low temperature processes. Directly you can integrate, do the integration on the packing also. And also they are biodegradable. And the very important advantage from general perspective, this opens a door to many exciting and advanced new applications that would impossible using the inorganic one. Here I can emphasize that the organic semiconductors have a high quantum efficiency, and it's easy to tune the wavelength of the emission property. This is very difficult whenever we go for the inorganic based semiconductors. So that is the main advantage of the go for the organic semiconductors. Okay. At the same time, why not? So most of the time, the organic semiconductors are based on the conducting polymers. Generally, the conducting polymers have a high resistance, therefore they are not good for the conductors of electrical conductivity. And the another very important disadvantages of the organic semiconductors are that it has a shorter lifetime, means easily it will degrade if we are not protecting it properly. If there is no insulation, proper insulation, then it is easy to degrade compared to inorganic one. But at the same time, so as I have classified the electronics before transistor, after transistor, here also I can classify the electronics before the invention of the conducting polymers or high quantum efficiency organic semiconductor, and after the invention of the high quantum efficiency organic compounds. In particularly, because of the organic semiconductors, the display technology got a very high impact, or the very drastic development happened in the display technology. Even because of the organic semiconductors, the flexible displays are also possible, and RFIDs also possible by the advantage of the organic semiconductors. And even nowadays, organic semiconductor based solar cells also possible. This is a very good advantage. In particular, one of the biggest application of use the organic transistor is the flexible displays. So in the previous case, or even now, so for example, if in this computer, all the transistors made of inorganic semiconductors. So generally you can make the inorganic semiconductor transistor, means you have to, the substrate you have to use as a glass or the metal. But if you want to fabricate the transistors based on organic semiconductors, you can fabricate the devices on the plastic substrate, then the flexibility will be very good. If you can flip it and you can hold it, that is possible if you go for the organic semiconductor based transistors. Okay, and compared to the inorganic one, can have a more brighter displays and thinner display and more flexible is possible whenever you go for the organic semiconductor based displays. And also in the future, the next question will be about what is the future? What are the things still we have to look for? So in the case of organic semiconductors, the smart textiles also is needed to be improved, and lab on chip and portable compact screens and skin cancer treatment. These all are possible based on the organic semiconducting devices. And one of the biggest challenge in the organic semiconductor based devices, organic semiconductor optoelectronic devices, is the organic lasers, which we are focusing here in ISET Tirupati in our research group also. So in general, if you think about organic electronics, means immediately come to your mind is the LED, the multicolor LED is possible. But here my question is, even though a flexible displays is possible, the thin displays are possible, everything because of organic electronics. But until now, the organic semiconductor based electrically pumped laser device is not existing in the universe. That is because, as I said earlier, the organic semiconductors have a low conductivity. Have an advantage is the high quantum efficiency, but at the same time, the conductivity will be very, very less. So if we look at the fundamental about what is the laser, how to produce the laser, the first laser was invented in 1960 by T.H. Maiman using the optical pumping. To generate a laser, we need gain medium, source, and resonator. But then the first inorganic semiconductor-based laser was invented in 1962 by electrical pumping. Again, you can compare this one as a vacuum tube, this one as a transistor. So in that analogy, you can use here also. So this one will be the very bigger in size. Whenever you go for the optical pumping laser, the output will be the same characteristics, but the total unit dimension will be very large, and handling also it takes very difficult compared to the electrical one. So the electrical pumping, whenever we design the electrical pumped lasings, it will be compact and more efficient to handle. Even nowadays, the laser devices are possible in a few millimeter size. So how about how to choose a compound if I want to? Because I said that here in ISET Tirupati, our lab, we are focusing on the development of organic laser devices. Generally, we can classify the semiconducting compounds in 3 categories. It depends on its pi-pi overlapping. If the pi-pi overlapping is very large, then the mobility, the carrier mobility will be higher, but the photoluminescence quantum will be very low. But if we want to make any optoelectronic devices, what we need is we need a good electrical conduction as well as a good quantum yield. So it is difficult to go for this either a small overlap or large overlap. So we have to choose a compound which have a moderate overlap, and we have to tune with the device structure to enhance its emission property and the conduction properties. So in that sense, so we are using the biphenyl trithiophene semiconductor organic single crystals as an active medium to generate the organic lasers, and we have achieved the very good organic semiconductor based lasers by optical pumping. But the real challenge is the electrical one. That one we are focusing on. So for example, this is one of the BP3T single crystal. So this is the crystal. So we are giving the optical pumping using the other light source. We are irradiating on it crystal. Then the laser is coming out of this sample from both the edges, the edge emitting laser. Okay, then whether the emission is the spontaneous emission or the stimulated emission, you can confirm with the optical studies. So for example, when you pump with a very low laser power, the full width of maximum is very large, is correspond to the red one. So when you keep on increasing the pumping energy, then the amplification starts. Once the amplification starts, then the spectral narrowing will be there. Then the monochromatic light you can expect from your system. That we have confirmed that this emission is a stimulated emission. But on the other hand, when we go for the electrical pumping one, also we can find the clear narrowing of the spectral narrowing is possible, but this is the semiconductor. So whenever you give the very high current into the semiconductor, there will be Joule heating. The Joule heating is restricting us to go further lowering of the...
Another 2 minutes?
Yeah, sure. Okay. So why suddenly I have discussed about these lasers? So because, again, I want to classify the information technology into before the invention of the laser and after the invention of the laser. Because of the optical communication, the backbone is the laser. So after the invention of the laser, the information technology industry has increased a lot. So now we are in the position to have a very high-speed internet, but in the future we are looking for artificial intelligence and deep learning, these things. So why we are discussing here this today is because of the India semiconductor mission. So if you want to know about what are the programs are going in our government of India taking initiation and what are the units recently they are opening. For this information, you can see from the Ministry of Electronics and Information Technology. In this web page, clearly it says that they want to bring the global hub for the electronics manufacturing and designing. India want to be a global hub for this. And for you people, this is very important for you guys, because after your graduation you have to look for the job. So which industry is very important, the globally. Okay, so if you see here, the global semiconductor market was evaluated around 550 billion USD 2023, and within the next 10 years it will go to 1,100 billion USD. So there will be a very good growth will be there. So it's a global picture. What about in Asia? So even in the Asia, because of the new, recent initiation of towards the semiconductor industry, Asia is also around 52% contributing in the semiconductor manufacturing industry. Okay, so this is a very important one. It can increase a lot of opportunities, job opportunities in the future also. This is very important. So with this, I would like to come to the conclusion. Just I have started with what is a semiconductor, and what are the intrinsic semiconductor and P-type and N-type semiconductor, the advantages of organic semiconductor, and what about the situation of the global and Asia semiconductor market size. Okay, with this, I would like to conclude my talk. Thank you.
Oh, it's too much.
Yeah. So let us thank Dr. Kanagasekaran for his very interesting introduction. And if you have any elementary questions, please ask. 5 minutes we can spend on questions, because we are also going to have manufacturing semiconductors in the country. I think Micron is coming up in a big way, and then Intel. So most of these computer chips and also mobile we are exporting. So if you have any 1 or 2 questions about semiconductors in general, use the microphone and ask. Ready? Good. I should have bought some chocolate to give it to you, but forgot.
Sir, is there any problem with inorganic semiconductors? Is there any problem with inorganic semiconductor, because why we have shifted to organic semiconductors?
The display technology is the very important. Okay, mainly the quantum efficiency of the inorganic semiconductors are just 1 or 2%. But when you compare with the organic semiconductors, the quantum efficiency you can reach until 100% also. Okay, but to get the equal amount of efficiency, you need a high power if you go for the inorganic one. The organic one, just few millivolts are fine to get a very good displays in these things. That is the main disadvantage and advantage.
So sir, the lasers are from organic.
Sorry?
So the lasers and all are from organic.
No, lasers are as of now. That's why I said the futures. We are looking for organic based, whatever is available now, the inorganic based one, we have to go for the organic one.
Yes, sir. Thank you.
Yeah, research is going on. So the inorganic one already moved to the industry. Yeah.
Thank you, sir.
Yeah, welcome. Sorry. Thank you.
Good morning, sir. Sir, my question is that right now in semiconductor, we have almost reached the atomic scale, we are at around 2 nanometer in the present day. So we are trying every day to shrink the size of the semiconductor and make them more and more efficient and pack more and more number of semiconductor in a small space. But as the limitations arise, we cannot go beyond certain length. So how are we going to deal with this issue?
It's shared. No, it's shared.
So with the quantum structure, Mm-hmm.
Yeah. So when we compare with the vacuum tube to the transistor in the same way, so if you use the quantum well device structures and the normal transistors, we can replace it. That is the only good option for to go for it. No problem. Yeah.
So such kind of things scientists are trying to.
Yeah. Still is need to come up.
Mhm.
VLSI, UL. Yeah, a lot of
Yeah.
things are there.
Yeah.
Yeah, it's going on.
Mhm. Okay.
Okay, we don't have much time. Short questions only we can allow. Finally, we are all waiting for Prime Minister's speech. So thank you, Dr. Kanagasegaran. Please give a big applause. So after Dr. Kanagasegaran's talk on historical aspects of semiconductors, now we go to another very important, curious connection between semiconductors and machine learning. So it's my pleasure to invite Professor Sen to talk to us about the connection and also the relevance of this. Professor Sen, please.
Thank you. Thank you, Professor Pillai. I will not be talking about semiconductors as such, but I'll be talking about machine learning. It's a wide topic, and I use it for my research. I'm not a sort of theorist or an expert like a computer scientist in machine learning, but I'll try to give you a flavor of where machine learning comes in, and I would emphasize this word paradigm and try to impress upon you that this is a new paradigm of research compared to the way you have learned so far, learned your science so far. Okay, now one of the words that Dr. Kanagasegaran used quite a number of times in his talk was materials. Now, materials define ages. This is a fact of history. Man's mastery over materials doesn't only define what he can do at a given point of time, but how the civilization progresses. So much so that various ages in history, as you all know, have been termed in terms of the materials which was most widely used for making tools. For example, the Stone Age, the Bronze Age, etc. Right now, we are in the semiconductor age, and that was the first talk about. What I'm going to tell you is that the next stage could be designer age, where we could be able to design materials, come up with materials which nature doesn't give us. Okay, we'll be producing, synthesizing materials as we need them. So, how do you discover new materials, for example, whether it's semiconductors or some particular metals? Quite often, it's serendipity or trial and error. You try various things and something works out, sometimes by design, sometimes again serendipity. In contrast to that, and all these approaches are time-consuming, expensive, uncertain. You do not know when success will come. But then what we are talking about today is that we rationally design materials that we need for a specific purpose. So those materials should have certain set of properties. I want it to be a semiconductor with a certain band gap. I want it to be a magnet with a certain magnetization or some other properties. So can we design such materials if nature has them? So there are two ways. One, maybe there are a bunch of materials from which I have to choose a particular one, which will be called screening of materials. So I screen a number of materials and choose the one that suits my purpose. And the other approach could be that I design new materials which doesn't exist. So in all of this, computation plays a very important role. So one of the approaches that is taken here is what is called high throughput computing. Those of you who are not sort of familiar with modern age computing in scientific research may not fully understand it, but still let me tell you that it's like you have thousands of materials. You want to calculate their properties based on whatever theory you know about them and want to choose the right one. Now, if you want to go one by one, I do this, I do that, it takes a lot of time. Instead, there is a sort of assembly line approach, almost an industrial approach, where you just one shot calculation. You go through all the thousands of materials, calculate all their properties, and finally you choose which one suits your purpose. That is better compared to doing blind experiments, but still computationally time consuming. Instead, here comes machine learning, where you can train what are called machine learning models, which can assist you in this screening. Instead of doing very expensive calculation based on your theory of physics or chemistry or whatever, you can use machine learning, which can give you those properties, predict those properties in fraction of a time. And finally, what comes is what is called inverse design of materials. This is a completely different paradigm of materials research. I'll come to that hopefully in the end. So I've already talked about this accelerated material screening. You could do computations, but they are still expensive. Then you could use machine learning, which are, in the particular application that we have done, at least an order of magnitude faster compared to doing full computations. So I'll now tell you a bit about what machine learning is all about. I'm sure many of the students would have some idea about what machine learning is, but let me nevertheless tell you. So when you type on your phone and it predicts what the next words could be, that's application of machine learning. That's something called natural language processing, which is used there, okay? In other cases, I'll try to relate it to something very simple you may have done in many of your lab courses. For example, you do some measurements and you try to fit a straight line or some other curve to it, okay? So now imagine you have a material whose some property depends on its pressure and temperature. And you have done a large number of measurements, you got that value and you have plotted something. And then you are told that, suppose the pressure and temperature is something which you did not have in your measurement. So what would be the value of that property at that pressure and temperature? What did you do is you look at that curve and you find the value of that curve corresponding to the new pressure and temperature values that are given to you. That's what is called prediction. This is a regression model. So the one class of tasks in machine learning is called regressions, okay? So you have done some measurement of a particular quantity which depends on some input parameters like temperature, pressure, etc. Could be something else, depends on the context. And then you are trying to predict some value. You have a large number of measurements or you have a large number of known cases based on which you are trying to predict what is the functional dependence of this unknown quantity in terms of these known quantities. So that is what regression is. That is the basic idea of regression type models in machine learning. Now, what this function is, how do you estimate that? These are matters of further details. So I'll not get into that. The other class of problems that we often face is we want to classify. A mail comes in, is it a spam? Is it a legitimate mail? A credit card transaction, is it a legitimate transaction or is it a fraud? These are classification tasks, okay? So we are doing two-way classification. There can be multi-way classification also. I'm told I have never used it. Some of you may know that if you take pictures of butterfly and upload somewhere on Google, it will tell you what kind of butterfly it is. So that is a classification. I'm told it can classify a large variety of butterflies. So these are classification tasks. So these two types of tasks are called supervised learning because you are training your model. You are predicting such functions based on a large number of known cases, large number of training data as they are called. So these are called supervised learning. There are other types of machine learning models, unsupervised learning, reinforcement learning. So I'm not talking about those things. Now, in the context of materials, I'll give you one or two examples. So for example, many of you would know about ferromagnets. You have heard about it, that they have spontaneous magnetization below a certain temperature. Above a certain temperature, they lose their magnetization. So that temperature is called the Curie temperature. And experimentally, a large number of materials and their Curie temperatures are known. And what these people did was to, based on some structure and composition information about these materials, which are matters of detail, and I cannot get into that, So they assume that the Curie temperature depends on certain structure and composition information of these materials. And can we predict from these known cases? So what they did was that, given a new material which has not been used to train this model to predict this function, can we predict its Curie temperature? So that's a machine learning model which, given a new material, can predict its Curie temperature. And that's sort of the plot of known Curie temperatures and predicted Curie temperatures. And similarly, you have a large number of materials and you want to predict whether something is a ferromagnet or an antiferromagnet. Okay, there are broadly two types of magnetic materials, antiferromagnets and ferromagnets. So can you classify them? Can your model classify them? Just like spam or not spam. So these are some of the applications, very elementary applications of machine learning in materials. So what are the challenges when you try to apply machine learning in materials? So machine learning model, any machine learning model, how it performs depends on quality and quantity of data. The more data you have, the better trained it is, the better prediction it will make. But garbage, if you put in garbage, you get garbage. So your data quality has to be good. So getting quality data in ample quantity in materials domain is a challenge. We don't yet have that. There are many experimental and theoretical databases for materials, many of which are publicly available. You can use those, but you cannot often mix those. And what is being done, and this is an interesting area of research, without getting into technicalities, one can still appreciate it. So I'm just mentioning it, is that, over 100, 200 years, many papers have been published in science. So a lot of information exists, but how do you extract that information? Okay. If you have to sit down and search each paper and note down the information, that will take a lifetime or many lifetimes. So here, what is being done is, again, what is called natural language processing. It's an area of machine learning. And models are being trained which can just parse through the published literature and extract the relevant information. And using that, you can create databases, material databases, which can be used for further research. So that's a very active area of research. And then the final challenge is, this is a bit more technical, that how you represent materials for your machine learning training, this thing. So anyone interested can talk to me later, but this is a technical point, so I won't get into this. So now I'll give you one example where we have used machine learning, is that, magnets. You look around and almost every electronic gadget, anything that has a moving part, has a magnet in it. Whether this is speakers, your mobile phone, laptops, etc., everything has a magnet. Now, when you use magnets, when you think about magnets, you'll think that, well, when there are so many gadgets which have magnets, then there must be a lot of magnetic materials around. Actually, that is not the case. So this inorganic crystal structure database, which is the largest experimentally verified database of materials, has about 10 to the 5, order of 10 to the 5 number of materials reported on it as of today. And if you will ask what are the number of magnetic materials, that is only a fraction of that, only about 1%, a few percent of that. But then if you want to use a material as a magnet at room temperature, you want its Curie temperature to be much higher than that, so that it doesn't lose magnetization very easily. And the ballpark number that is taken in the sort of technology community is that the Curie temperature has to be at least 600 Kelvin. Turns out that number of magnetic materials with Curie temperature 600 Kelvin is very few. There are not many materials. But then you also want some other properties of these magnets. You want the magnetization to be fairly large so that it serves your purpose. And then there is something else which is called magnetic anisotropy. So this is a very sort of complicated concept, but let me tell you very briefly, quickly what it is. when you think of a magnet, a ferromagnet, what happens is that all the magnetic moments on all the atoms inside the material point in a certain direction. That's a very simple picture of a ferromagnet. Now, why in a particular direction and which particular direction? That's an important question. They prefer a particular direction in most cases. They prefer either a particular direction or a particular plane. They don't usually orient in any random direction. Now, what you want is that you want materials in which all the magnetic moments are pointing in a particular direction. And if you try to rotate them in the opposite direction, that should cost you a very high energy. That's the kind of materials you want. And that is called magnetic anisotropy. So you want materials that have very large magnetic anisotropy energy. So if you try to fit all these conditions, I'm not going into commercial aspects of cost, etc. That itself is a big scientific technological challenge. Then also, most of these magnets with large anisotropy contain rare earth elements like neodymium, cerium, etc. And that is a problem because countries like, most of the Western countries and India, we do not have access to many of these rare earth elements. China has lots of reserves of these rare earth elements. So that's another problem. So therefore, what we want is permanent or hard magnets with large magnetization. Hard magnets are those that have large anisotropy energy. We want permanent magnets with large anisotropy, large magnetization, large TC without rare earths. And that's a very, very big challenge. Okay? But that's where machine learning can help us. So this is I have tried to summarize something that we found out. So what we found is that there is a publicly available database of materials, most of them magnetic. So this big circle is the set of all these materials, okay? But out of those, for a tiny fraction, a very small subset of those materials for which this anisotropy information was actually reported in the database. So then we ask the question, if we have so many other materials, does any of those have also large anisotropy? The ones that are in this part of the subset, this subset? Now, of course, what one could have done is taken these thousands of materials and done whatever calculations, quantum mechanical calculations we can do. But that would have been very expensive computationally. And so therefore, what we said is that now let us use our machine learning models to find out, to predict how many of these materials would actually satisfy our requirement. So then what we did, without getting into a lot of technical details, what we did was we used a series of machine learning models. Is this material stable? Is this material, does it have a large magnetization? Then does it have an anisotropy so that, magnetic moment tends to align in a particular direction? So all these things were checked and predicted by several machine learning models. After that, these machine learning models predicted that there are 14 materials out of these couple of thousand or 3,000 materials in this part of the set, which satisfy these conditions. So then we did expensive quantum mechanical calculations only on those 14 materials. And as it turned out, 10 of those were found to satisfy all the conditions that were required. So this is the power of machine learning model. Okay, so with that, we come to the last approach, which is called the inverse design of materials. It's a completely different approach. It's a completely different paradigm. Now, the kind of things I talked about so far is what you do is, given a material, you know its structure and composition. Material is used in a very general sense. It could be a molecule, it could be a solid, it could be whatever.
but you know its structure and composition. And you know some theory, right? It could be quantum mechanics, it could be something else. And so given this, you try to calculate its property. Given a material, given a semiconductor, I try to calculate what is its band gap. Okay. So that is the theory-driven approach. In the example that I showed you, we used it. These machine learning predictions are what is called a data-driven approach. That I don't care about the underlying theory. I train my machine learning model so that it guesses what the underlying relations are and then predicts the properties. So that's a data-driven approach. That's why in that approach, if you have garbage data, you have garbage results. So it's very important to have quality data. This new paradigm I'm talking about is completely inverting this problem. I am not going from materials, structure, and composition to properties. I'm asking, if I want a set of properties, what kind of material, structure, and composition should I have? So I'm completely inverting this question. Now, if this comes as a sort of surprise to you, I'll give you examples that you may have come across, at least in news items. There were reports that some AI-generated art got some award in some art competition. So these are done by using what are called generative machine learning models. They can generate new content. If any one of you has used ChatGPT, you know that it's a generative model. It's a generative model trained on languages. So what we are going to do is to train a generative model which can generate new materials. So there are at least 3 widely used generative models that I can think of, or 2 or 3 generative models that I can think of right now. So the particular one we used is based on what are called autoencoders. Now, autoencoders, I will not get into too much of technicality, but autoencoders use what are called fine. Sure. Okay, so our approach is based on autoencoders, a little a variant of autoencoders, which are called variational autoencoders. Now, I will not have the time to sort of explain to you. In a non-technical manner, I would have liked to explain this to you, but anyone interested can talk to me later. So what it does here is that it takes a sort of image here, reduces to a smaller dimensional representation and tries to take it back to its original representation. Now, why does one do it? Is that, when you, in the smaller dimensional space, you can take sort of points from this low dimensional space without bothering about what was on this side. You can take new points in this low dimensional space and try to sort of decode it. This part is called a decoder, this part is called an encoder, and decode it to new images. So if you take new points from this lower dimensional latent space, you get new contents on the right-hand side. So therefore, if you train this model on a particular class of objects, in which, in our case, we train these on some materials images. So when we take new points from this latent space, we get new materials. So that's the way. I'll just skip these details, and I'll just show you that these are the 2 materials that we obtained. These materials did not appear in were not there in our training data set, and they were not in any available data set. These are new materials theoretically predicted, which satisfy all the conditions that we wanted. So with that, I'll stop.
Yeah, please let us thank Professor Sen for his very interesting talk. And now we connect you to Delhi. Maybe in the end, we'll have some question answers, or they can ask you questions, afterwards.
Sure.